Hello everyone, welcome to Chaitanya Academy, and I also welcome you to this transition course where I was discussing with you some basics of chemistry that will land you ahead of all your batchmates so that you have a good start in 11th. So now let's get started with today's topic, which is the electronic configuration, rules or electronic configuration. In today's class, we will learn how to write the basics of electronic configuration, how electronic configuration works. And mind you, if you are a pro at writing electronic configurations, you will be able to solve many questions, many concepts, and many reasons for things happening in chemistry come from this electronic configuration. So pay special attention to it. The electronic configuration basis starts from orbital. In the last class, I finished at this, right? Orbital. Now, what is an orbital? First, let me define it. So what is an orbital? An orbital is an area, or not area, I should say volume, is a volume around the nucleus where probability of finding electron is, according to NCERT, 90%. So it is just space or area. So suppose you have nucleus here and this is a space, right? So I can say, you are unable to see. Please check your internet connection because everything seems fine from here. If you are unable to see, right? Because things are fine from here. So this area which you are having, this area is called an orbital. Right. What do I mean by probability? I mean that if 100 times I make a guess that electron is here, electron is here, electron is here, 90% of the time my guess of where the electron is will fall in this region. Okay, if 100 times I guess, okay, if I ask you the question, where is the electron around the nucleus? If I guess that, okay, electron one time is here, one time is here, one time is here, and then I guess the electron is here, 90% of the time electron will be in this region, right? Similarly, you can understand it in that way also. If I have a camera which can see electron, right, and the electron is moving fast, it is moving here and there, and I tell the electron to stop, like the statue game which we play, statue, you will find that 90% of the time electron will be inside this sphere or inside this area. Okay, so that is what I mean probable radius. Similarly, if a small child is there and there is a park boundary, right? There is a park boundary. Suppose this is the boundary and you enter from here and there is a small child running. So we can clearly say that 99% of the time the child will be inside this area. Correct? The child is electron here and 90% of the time that child electron will be in this area. That area or that volume is called an orbital. Okay? And that orbital is defined by what? Remember, m value. Right? Each orbital will have a m value. Okay? And each m value represents an orbital. Yes. Hi, Aman. Right. So each orbital has a m value, which we already know from the last session. People who do not know, please refer to the last session. It is there for your reference. Right. So orbitals, so let us take for n equals to 3. For n equals to 3, L value can be 0, 1, 2, right? and for 0 the m value can be 0, for 1 the m value can be -1, 0, +1, and for 2 it can be -2, -1, 0, +1, +2, right? These, and each value of this represents a orbital, right? Now, how to write that orbital is also what I taught you. How do we do it? N, right? And here, depending upon the value of L, if it is 1, it is P, right? If L equals to 1, it is P. If it is 0, it is S. If it is 2, it is D. 3, it is F, right? So that is what we learned. So N, now what value of M it has? If it is 0, then S, okay? Now, in which direction the orbital is? NS doesn't have any direction. Here N is 3, so it will be 3S. On the basis of that, I also talked about p orbitals. P orbitals can be p x, y, or z, right? X, y, and z. X, y, and z, right? So when you have p orbitals here I can define 3 p orbitals, right? 3px, 3py, and 3pz, right? Where each of them represents these values, right? This should be there in your mind. So if 3px is written, which x, y, or z, which will have +1 or which will have -1, that should not be your discussion, that should not be your focus. But remember, one of them will have 0 as m value, one will have -1, one will have +1, right? So after this background, right, we are ready to understand the energies of orbitals. Now, energies of orbitals are different in 2 cases mainly. So 2 cases you will have, right? The first case will be hydrogen-like atoms. Hydrogen-like atoms are the ones which have only one electron. Because hydrogen has one electron and one proton, so hydrogen-like atoms are the ones which have only one electron. So if they have one electron, then the rule of thumb is orbitals with the same n value have same energies, right? So what I'm trying to say is, if you have 1s, right, two s, 2p, 3s, 3p, 3d, right? So you can see 4s, 4p, 4d, 4f, right? You can see if the orbital has same value of the principal quantum number n, the energies are same, right? The energies are same. This, mind you, keep in mind, is only true for H-like atoms which have only one electron, right? So the energy is directly proportional to your n value, right? So if you have higher n, higher is the value of n, higher is energy, right? Higher is the value of n, higher is energy for H-like atoms. Now, if I move forward, right, to other kind of atoms, case 2. Now, before doing that, you have to understand the concept of shielding. So what does shielding means? It is derived from the word shield. What is a shield? Shield is an instrument that protects you, right? Protects you from danger, right? Just like in war we had a shield so that the sword cannot cut us into pieces, same way shield. Exactly or quite similar is the shielding effect. To understand the shielding effect, let me give you an example. So here you have the nucleus and then you have here your orbitals, okay, whatever it may be. Now I have electrons, right? So here I have an electron, here also I have an electron, right? Suppose electron 1, electron 2, and outside I have electron 3, okay. Now think of it as this nucleus as your enemy. So this nucleus is your enemy, right? If nucleus is your enemy and I am focusing on electron 2, tell me which electron 1 or 2, which electron can shield this electron 2 from nucleus's power? Which electron 2 or electron 1 or electron 3, which electron can shield electron 2 from the power of nucleus? What is nucleus doing? Nucleus is pulling this electron towards it, right? Nucleus is pulling. What do you think? Which electron can do it? Electron 1 or electron 3? Simply pay some stress on your minds. Only and only electron 1 can help. So I can say that electron 1, like a shield, is standing between the enemy and the victim and protecting this victim from here, right? That is the absolute reason of what shielding actually is, right? So what is the power of nucleus that this electron 2 feels? It is the nucleus's attractive pull. So the nucleus is trying to pull this second electron towards itself, but the inner electron is preventing that. How exactly? Common sense, think about it. Both electrons are negative charged, right? So now moving into the domain of physics little bit. So this electron 1 is getting pulled by the nucleus in this direction. Let me take another color. Right. But, no, sorry, electron 2. Sorry, electron 2. Right. Let me just make it a little bit more understandable. You have electron 1 and you have here electron 2, correct? Right. Now on this electron 2, and here is the nucleus is pulling this electron 2 in this direction. But simultaneously this electron, because it is also negatively charged, it will repel this electron in this direction. Can you see the yellow arrow and the white arrow are acting in opposite directions, right? Because this is a electron repulsion, this is nucleus electron attraction, right? Opposite direction acting. So what happens is this attraction is little bit reduced by this repulsion, and that is what I mean by shielding. It shields the electron, it shields the So shielding, if I want to define shielding, how will I do that? The inner electrons, let me just define it in the next slide. Okay, let us do it here. If I want to define shielding, Now this shielding also not only happens by the inner electron, if there is an electron here also, this also repels and actually protects it from nucleus pull. Inner electrons shield or reduce the nuclear pull on the outer electrons, and hence the outer electron feels, the word I am saying feels, a reduced nuclear charge called ZEFF, where EFF means effective. So the outer electron feels what? The outer electron feels that the nucleus's charge is little less, right? That is called Z effective, right? So Z effective is equals to actual nuclear charge. This is atomic number, for that matter, let me tell you, this is atomic number, minus this is your shielding constant. Shielding constant, right? So this is called shielding. Now this shielding effect can operate only when you have at least 2 electrons, right? You need at least one soldier to protect you. So you are one electron and the soldier is another electron. Both are required for protection. That's why this effect does not work in single electron species. This effect does not work in single electron species. Now, what happens because of this shielding? Because of this shielding, right? So let me take one more slide here. And consequences of shielding. Because of this shielding, now same n orbitals don't have same energy. Okay. This is now for more than one electron species, right? More than one electron species. So, how do we decide that? It is based on the n plus L rule. Now, this rule says that higher is the value of n plus L. So, higher value of n plus L, higher is energy of orbital. Higher is the energy of orbital. Next it says that for same n value, for same n value, higher L has more energy. Okay. So, based on this, right, this is actually the criteria for energy. We have order of energies, right? Criteria for filling, let us change this to order of energies. Order of energies of orbitals. Now, how will you get to that order? See, this order is mathematically calculated and also determined experimentally. Through experiments, it has been determined. So, how to keep it in memory? There is a trick for you, right? There is a diagram, right? Let us draw that diagram along with me in your notebooks, right? So, you have like this 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, then you have 6s, 6p, 6d, 6f, and finally I have 7s, right. So draw this out. Now comes a way of doing this. So how to predict the energies? Start from here, okay. Draw a, 1 minute. Draw a straight arrow through 1s, right. Then through this narrow path, go backwards. Draw another straight arrow through 2s. Now again through this narrow path, go backwards. Draw a straight arrow through like this. Then again go backward through this narrow path. Draw a straight arrow through here, right. Then again through the narrow path, go backwards. Draw the arrow through 3d, 4p, 5s. Then again through the narrow path, sorry, go backwards, draw a straight arrow through this, and then you can keep on following this through this, and finally this, right. Okay. Based on this, I can write the energy orders. Let us do that. So the first lowest energy one will be order of energies we are finding. So you have, let me just do it. Follow your eyes, 1s, right, least energy, followed by next is 2s, going back 2p, 3s, 2p, 3s, 3p, 4s, going back 3d, 4p, right, 3d, 4p, 5s, going back 4d, 5p, 6s, and after 6s you have 4f, 5d, right, 6p, and then you have, sorry, 7s. Like that you can continue. This is the order of increasing energies of orbitals. Keep this order of increasing energies in your mind, because what is the topic? Today's electronic configuration, right? When we go to that topic, this will be right. Unable to see, I don't know what is the issue with your internet connection. Are others also not able to see? Please respond. Anil, I don't know why you're not able to see. Most probably you should be able to see, right? There's nothing wrong with my internet connection here, nothing wrong with the camera here, right? So keep this in mind and let us move forward to Aufbau's principle. Now, even before that, 1 minute. Now, why of next, what we are going to do is, now understand that each atom of an element has electrons in it. So now we are going to learn about the rules. What? Rules to fill electrons in the orbitals. Right? These are mainly 3 rules. Right? I can see. Okay, someone can see. Anil, then there is a problem in your internet connection. Kindly rectify it, see it. The first one is Aufbau's principle. Second one, Pauli's exclusion principle. Third, Hund's rule. Hund's rule of maximum multiplicity. Right. So these are the 3 rules according to which you will fill electrons in the orbitals. Right. So let us go at with the first one. In the ground state of atoms, ground state means when the atom is not excited, the orbitals are filled in order of their increasing energies. That's why we have learned this. So now you are going to fill orbitals in order of their increasing energies, right? The one with the lowest energy first fill this, then fill this, then fill this. So that is what I mean by Aufbau's principle. So you can decide this energy based on N plus L rule or L rule. I have already discussed this, right? Next is Pauli's exclusion principle. Pauli's exclusion principle tells us what? See, this line will be written, no 2 electrons in an atom can have the same set of 4 quantum numbers. What are the 4 quantum numbers? N, L, M and small s. Right? These are the 4 quantum numbers. So what do I mean? I mean that no 2 electrons can have the same address. Other words, 2 electrons cannot have same value of all 4 quantum numbers, right? So every electron needs to have different values of at least 1 quantum number. Now let us understand that with an example. Suppose this is an orbital. Orbitals are normally in books represented by these square boxes, right? So let us see how can we understand this. And electrons plus half spin like this, minus half spin will be like this, right? So this is your plus half, doesn't work, okay? That is minus half, this will be understandable, right? So if I have a situation like this, right? Now let us take another one. Many situations we will take. Suppose I have a situation like this. Let me take one more situation. Like this, like this. one more situation. Right. So this in this one, right. So now let us see how it helps. Now let us write the value of quantum numbers for each of these situations. Suppose this orbital is 2px. Right. So n will be for this 2p. So suppose this p is for L equals to plus 1, right? So now L first will be 1 and m will be plus 1, right? Plus 1 and it is pointing upwards, so s will be plus half. All four quantum numbers, right? This is single electron. Pauli's exclusion principle comes into effect when more than one electron is there. Here, again n will be equals to 2, L will be equals to, for this electron. For every electron there will be a different values of quantum numbers, that is what it says. Now L will be equals to again 1, m will be equals to plus 1 only because I am considering that this is x is for plus 1, s will be equals to plus half. Now for the other electron, if I take the value of n, will be 2, 1 plus 1 and again it will be plus half. Right. Let us see this situation as well. Here n value will be what? N value will be 2, L will be 1, m will be plus 1 and s will be plus half for this one. For this one again n will be 2, L value will be 1, m value will be plus 1, but because it is pointing downwards, the s value will be minus half. Right. Next, this one, you have 3. So this for this one will be 2, 1, plus 1, plus half. For this one will be 2, 1, plus 1, minus half. For this one will be 2, 1, plus 1, plus half. Right. Now let us understand. Is green visible? Yeah. What all things is possible and what all things are not possible. Pauli says that two electrons in the same atom cannot have the same value of all quantum numbers. Now here these are the value of quantum number 1 electron or 2 electrons. Can you see all the 4 quantum numbers are same for this? So this situation clearly is not possible. Right? Moving on to this. N is same, L is same, M is same, S is this same? No. It's plus and minus. So this situation obviously is possible. This is possible. Right? Understand that because they are in the same orbital. Each box represents the orbital. Because the orbital is same, the n value, the p value, L value and the m value are already fixed. Right? So these values are already fixed. You cannot change them because these values are decided by the orbital. These values are decided by your bench. Right? If on the bench in your class 2 people have to sit, right, that bench decides the value of n, L and m. Only the value of spin is not decided by that bench. That is decided by the electron. So here also you see these values are same, but this is different. This is also same here, different. Now moving on to this. Here see, different, possible, but the problem is the third electron again has the same value, right? So this and this have the same value. So this situation is also not possible, right? So each situation you have to convert into logics. What is the logic there? Only and only this situation is possible, right? So see, if I add more than 2 electrons in an orbital, understand that here there can be one more situation. Suppose one more situation for you. This is up spin, pointing up, pointing down, pointing up, pointing down. I can also do one more pointing down. Again, these two will have the same value of same all 4 quantum number. So this situation is also not possible. So no matter what you do, you cannot add the third electron in an orbital, right? Only 2 electrons are possible in the orbital. So this fixes the number of electrons that can occupy an orbital. 1. So number of electrons in an orbital are fixed to 2. So I can say that number of electrons in one orbital maximum can be how much? 2. Second thing, see, even with 2 electrons, they cannot be pointing in the same direction. This is also not possible, and both down also not possible. So an orbital can contain 2 electrons, yes, but not pointing in the same direction. They have to point in the opposite directions. So I have to say number of electrons in one orbital maximum should be 2, but with opposite spins, right? And this inference is given in the next. So this is the working principle. The inference from Pauli's exclusion principle, PEP. And this is what is used in filling the configuration. So simply what I'm trying to say is you can only fill 2 electrons in an orbital, and that too with opposite spins, right? So remember that one orbital box is an orbital. So this is your orbital, and in this orbital you can fix only 2 electrons with opposite spin. So this is your correct representation and the only possible one. Now this was confining us to one orbital. Now I'm moving on to more than one orbital through Hund's rule of maximum multiplicity. Now this rule tells us that, let us do this. Out of different arrangements of the same electronic configuration, the arrangement which has higher multiplicity will be more stable. Let us understand. Let us take what are these? Px, Py and Pz, right? So now, suppose now I have to fill 3 electrons. So I can fill the 3 electrons like this or like this, right? Any other way? Like this only I can fill, right? Now each electron has a spin. So this electron has plus half spin, this also has plus half, this has plus half. Here this one has plus half, this one has minus half, this one has plus half. If you add these spins, means I take addition of all the spins. This is given as a value of capital S. If you add all these 3, you will get 3 by 2 here. Here you will get S as 1 by 2. Right? Now, what is multiplicity? Multiplicity is 2 of this capital S plus 1. So in the first case, if I talk about the multiplicity, how much it will be? 2 multiplied by 3 by 2 plus 1. Okay. Right? How much it will be? 4. Here the multiplicity will be 2 into 1 by 2 plus 1. How much? 2. Which has a higher multiplicity? this situation. So this situation is most stable, and this will not happen, this will happen. Now for this to happen, remember that in the absence of magnetic field, I told you, these three orbitals will have same energy, and same energy orbitals are called, there is a word, degenerate orbitals. Right. So if you have same energy orbitals, degenerate orbitals, then if you need to add electrons, you will add electrons in the same spin, one by one in each orbital. First, single. So single here one, single here one, single here one. After each orbital is occupied with one electron, only and only then you will add the next electron in the orbital with opposite spin. So if I have to fill here 4 electrons, I will add here like this. So what I am trying to say again, let us see. So suppose now I need to fill 5 electrons. So what should be my way of filling? These orbitals are degenerate of same energy. 1, 2, 3, 5 electrons we have to fill. So 1, 2, 3. First fill all of them singly. 1, 1, 1, 1 in all in the same spin. Then 1, 2, 3, 4 and 5. So fill them. This is Hund's rule of maximum multiplicity, which says that, now this you will understand. Pairing. Pairing means what? Pairing means this. This is pairing, right? So now this explanation will be understandable. Pairing of electrons. This is the used version of electrons in the orbitals belonging to the same subshell, right? Same subshell, P, D or F, does not take place until each orbital belonging to that subshell has got 1 electron each. They have to be singly occupied first. So singly occupied first, then double. Right? This is your Hund's rule. Right? Now, how does it apply to electronic configuration? Now, what is electronic configuration? Nothing. You have a bunch of electrons in an atom. How and where are you going to fill those electrons is called electronic configuration. Right? Let us take an example. Lithium, atomic number is 3. It has 3 protons and 3 electrons. So 1s, 2s, 2p. Now this filling will be according to, remember, according to this. This slide you should bookmark, keep in mind. Right. Moving on. Lithium has 3 electrons, so you will fill how? See, understand that S energy is different from 2s. 1s is different from 2s. So that rule of single occupation is valid only for same energy orbitals. Right? So you will put 1, 2, and 3. Right? So if I have to fill 1, 2 and 3. Similarly for beryllium, I will add how? I will add 1, 2, 3, 4, because number of electrons are 4. Boron. Now boron has 5 electrons. So how will you do that? 1s, 2s, 2p. So 1, 2, 3, 4 and 5. Right? 1, 2, 3, 4 and 5. Similarly, carbon has 6 electrons. Now 1s, 2s, 2px, 2py and 2pz. So 1, 2, 3, 4, 6, 5 and 6. Okay, that's why 5 and 6. Nitrogen has 7. So 5, 6, 7. Right. Oxygen has 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right. Fluorine has 9. 9. Neon has 10. So all of them are filled. You can write this like this, or you can write 1s2, 2s2, 2px2, 2py2, 2pz2, Remember, the energy orders are like this. Here, this is equal. Okay, like this also we can write. Noble gases. So why noble gases are important, right? You have helium, neon, argon, krypton, xenon, radon, right? If I write their atomic numbers, helium is 2, right? 10. So there are numbers for getting that. 8, 8, 18, 18. So 10, 18, 36. So you have 36 plus 18. 54, right? And so on and so forth. You can get the values. So now, so why this is important? This is important because when you go to higher numbers like zinc, right? How will you write the configuration of zinc? We have little less time. So I'll go directly to the configuration. Right. This is zinc. Right. So if I take zinc's electronic configuration, which is 30 atomic number, how will we fill it? So 1s2, 2s2, 2p, 6, right? 3s2, 3p, 6. 4s2, right? How much it is over? 6 plus 4, 10 plus 4, 20. Now 20 is over. After 4s2, what will come? If you see the Aufbau principle. Yeah, even I have to refer this. After 4s, 3d and 4p. So now you will have 3d. So d orbital can have how many electrons? So d L value is 2. So number of electrons will be 2. L value is 2 plus 1 multiplied by 2. Right? 4 plus 1, 2, 5. So d orbital can have 10 electrons. So now you have 3d, 10. 3d, 10. So how many are there now? 30. 30 are over. Right. So there is another way of writing this. Check till where you are getting the noble gas configuration, right? You are having here 10 plus 10, 20, right? So 20, is there a noble gas before zinc which we can use? Think about it. You can see here argon having 8 electrons, right? 18 electrons, sorry. So what I can do is, this is 10 plus 6 plus 2, 8. So this is 18 electrons. This complete 18 electrons I can write by square bracket here. Argon for these 18 electrons, and rest I can write 4s2, 3d, 10, right? I can also write the configuration like this or this, right? Sir, unable to see. Vamshi Yadav, it is for NEET also. Yes, it is, right? I don't know why people are unable to see. Please upgrade your internet connection. The internet connection maybe is not working for you. So like this you can write, and like this, based on the atomic number, these are atomic numbers, you can write configuration for all the atoms which are found in the periodic table, right? So this you can take it as a homework. Tellurium, chlorine, right? Now, stability of fully filled and half filled orbitals. So, normally we say that if the situation is of a fully filled orbital, it is much more stable than half filled. So, we talk about the stability of configurations. Fully filled is most stable, followed by half filled, followed by partially filled. What do I mean by this? Let me give you an example. Right? So, fully filled means fully filled 1, 2, 3, 4, 5 and 6. Fully filled. Half filled means only one electron. Partially filled means this, or it can also mean the fully filled configuration is much more stable than half filled and less stable than partially filled, right? Now, because the time is running out, what I'll do is, I will cover this part in the next class. Let us not hurry into stuff that we will not be able to understand. The reasons for why this is, you will get in the next class. So, for that, you need to join the next class, my dear students, right? Without that, right? So, keep your appetite hungry, right, for the next class. By the time next class comes, note this down tables and try and write down these configurations. There will be some exceptions where there is a star here, right? This star, this star. Don't pay heed to exceptions. Write what is not exceptional. And I will meet you in the next class. Before I end this session, pay your attention on this Google form. Fill it up so that we are able to bring to you new concepts and new classes. So please scan this out, right? And to get some more PDF of this complete session and some more revision notes and also some more questions, right, for your practice, join this Telegram channel. Please, I urge you to join this Telegram channel. There is a lot of information here which is completely free. Join this out so that it helps you in your preparation, right? So, bye from my side as a chemistry faculty at Sri Chaitanya Academy. Next, we have math session for you, right, where you will learn a lot about the topics in maths. I don't remember what topic it is, but wait for it. Till the time you are waiting, please scan both of these forms, join the Telegram channel and fill in the Google form. So, bye-bye from now.